So what is the essence of statistical mechanics? Well, in classical mechanics, we learn how to describe single particles, right? So if I have a particle and I know its position and its velocity at a certain point in time, and I know the forces acting on it, then I can fully describe its motion using Newton's laws of motion, right? So I know how to solve this problem. This is already solved, so to speak. So, what if we consider a system of many of these particles? 10 to the 23 of these. How do we study this? We are actually interested in its macroscopic properties such as temperature, pressure, and volume. So, how do I use my knowledge of classical mechanics to describe a system like this? In other words, how do I connect the microscopic world to the macroscopic? Because surely, if I know how to fully describe a single particle in a system, I should be able to uh, describe the whole system, right? And I should be able to get these uh, macroscopic properties that fully describe it. So, how can I do this? Well, one way is to try to describe each particle individually. So, let's take this particle and write its equation of motion. Okay, and then I can do the same for this particle, and the same for this, and so on, until I fully describe the system. So the problem, as you can see, is that we have 10 to the 23 particles, so this is really tough and not viable at all. So to solve this problem, we have to use a different approach. And to illustrate this, I will step out of physics for a moment and consider a problem in demographics. So if we have a population, and as it usually happens in demographics, we want to study certain aspects of this population. We will not go with each individual and learn about its specific history to describe the whole population. That would be really time consuming. What one usually does is to use averages and to use this powerful branch of mathematics which is called statistics. That is the same thing we will do here. So we will not learn about each single particle in the system. That would be really time consuming. We want to learn, we want to study the statistics of this system. So we will use our knowledge from classical mechanics. We will apply statistics on that knowledge, and then we will obtain the microscopic properties of this whole system. And that is the essence of statistical mechanics. And that represents a connection between the microscopic and the macroscopic. Okay, sounds great, but how do we actually do this, right? Let's consider a system. A system of many particles, uh, how do I apply statistics to describe it? So let's go back to the example of this population. So let's say we want to know whether this population is mainly composed by young people or old people, or in other words, the average age of the population. So I could go with each individual and ask about their age, but this is really time consuming, right? We are looking for another approach. So the idea is to consider all the possible ages in the population. So for practical purposes, let's say it's from 0 to 100 years. And then one finds the probability associated to each age. So for instance, it having 20 years might be more likely because than 100 years, because people usually die before reaching 100 years. That is more of a demographics argument. It doesn't really matter. That's not the point. So the point is that if we have these two pieces of information, we can describe the system statistically, right? With the probability and the possible ages, I can get the average age. So it's exactly the same for this system of many particles. How do we describe it? We could go with each individual particle and learn about its position and velocity, but that's time consuming. That's really difficult. So instead, we consider the set of all possible states, all possible configurations or states of the system. And what I mean by that is that particles might be arranged differently in different states. So in a different state, this particle might be here, this particle might be here, and so on. So that's the idea. And then the probability of having each state. If we know this, again, we can compute averages of quantities that we are interested in. So for instance, energy or temperature. So that's the idea. How do we get the set of all states of the system, of all possible states? Well, we go back to the description of a single particle. So this particle, we consider for this particle all its possible positions and all its possible velocities, and we do that for each particle in the system. This might look more complicated, but bear with me. So we do that, and we get this collection of possible states of that represents all possible positions and velocities, right? So this might have a certain configuration, this might have another configuration, and so on. So this collection of possible states is really large, but we will do statistics on it, just as we did statistics on the population. And from this statistical analysis, we will obtain the relevant uh, the relevant macroscopic properties of the system. And this is the essence of statistical mechanics. So now I will introduce some important terminology. This collection of states, of possible states, is called an ensemble. And this is a key concept in statistical mechanics. The specific terminology we use for ensembles depend on the system. So if the system is isolated from the rest of the universe, if it cannot exchange energy or matter, then it is called microcanonical ensemble. So if the system can exchange energy but not matter, the ensemble is called canonical. And if it cannot exchange neither energy nor matter, sorry, if it can exchange both energy and matter, then we have a grand canonical ensemble. Now, I've been talking about the set of all states, of all possible states of the system, but I also mentioned that the probability is needed to do statistics on this set, the probability associated to each state. And I haven't talked about this probability. So what do we do? Well, it turns out that this probability is different for each ensemble. So for the microcanonical ensemble, each state is equally probable. For the canonical ensemble, each state, the probability of each state depends on the energy. And this actually leads to the so-called partition function. Partition, which is a key concept in statistical mechanics. I will not go into details right now. I will do that in further videos, but this is the big picture of things. And the grand canonical depends, the probability depends on the energy and the particles. And particles. And this leads to the grand partition function. Okay, so to sum up, we have a system of many particles, and we are not interested in tracking each and every single particle to describe the specific state the system is in at a very specific time. Instead, we consider the set of all the possible states the system can be, and the probability associated to each specific state, and from that we use statistics to obtain the macroscopic properties of the system. So this is what I wanted to talk about, and I hope it was helpful.